So we want to talk a little bit here about some of the properties. Now we won't have time to get through all of the properties in the system, but there are a few things that I think are important for us to think about. In general, we need the cement and the SCM to react. So we start out with a whole bunch of cement particles. For some reason, they became white cement particles here. Over time, the system starts to hydrate. In general, what happens is fuzz grows on the cement. All right, this fuzz is calcium silicate hydrate. It's a little bit like Velcro, and it starts to connect those particles toward one another. And then the system will start to develop, right? That fuzz will keep growing, and what happens is this blue space is the porosity in the system that really decreases over time. As porosity decreases, strength goes way up, transport goes way down. Right? So the whole game here is about controlling porosity. Right? The whole issue here, we want to get water to react more of those cement particles and reduce the porosity. So there was a question a little bit earlier about what happens when you have internal curing. This is a measure of the amount of hydration after 3 days. We typically see about 7% higher hydration, and this is below 0.4 water to cement ratio even by the time of 3 days. Right? If we take this out to 28 or 91 days, we'll see about 10% maximum here, but the band becomes much more uniform as we work our way up the overall graph. Right? So we're increasing that degree of hydration. I talked earlier about the fact that the hydration stops when you get to 80% humidity. Right? A lot of people really learned this when I started saying this 15 years ago, and they said, if I've got water, everything's okay until I get to 80% humidity. That's not exactly true. This is a pretty old plot that came out of the Portland Cement Association in the 1940s. This is how much hydration you have when you got plenty of water. This is where hydration stops at 80%. You will notice that hydration drops off considerably as you go from all the water you need to 80%. So if you stopped off at 90%, you're getting about half the hydration rate that you should be getting. To do something that looks more like real concrete, right, we frequently don't take one of these bridges and place it underwater for 28 days until we test it, providing it all the access to water. Right? We saw pictures earlier where we don't even take care of it for the first 6 hours. Right? So we've always argued that to really see the benefit of internal curing, you want to see sealed samples. Right? Take that sealed cylinder and use that sealed cylinder. Now, it turns out if you take your internally cured concrete, compare it to your water cured concrete, those numbers stay the same. If you compare your internally cured concrete to your water cured concrete to the one that's kept out on the slab, you typically see, depending upon the mixture, an 8 to 30% reduction in strength. These are just data to tell you about what the relative humidity is inside of the samples, and this is the type of graph that starts to take you through. If you water cured everything, you get the same strengths at 7, 28, and 90 days. If you looked at water curing versus a drying environment, you see a big difference. But here you'll see this is the internally cured concrete, this is the plain concrete, this is the water cured concrete. You see that your internal curing matches your water cured strength pretty well. All right. Some key takeaways, you can read all this on your own time. A lot of people are very worried about the fact that the lightweight is going to reduce strength, but I do want to just point everybody out to the fact that, point out to everyone that lightweight aggregate's been used in a lot of high strength concrete. All right, and there's no reason why we can't make higher strength concretes if we want to. I will also make the comment that one of the things that the lightweight does is it changes this thing called the interfacial transition zone, all right, the ITZ. Now if we look at this, we can think about the fact that we typically have some paste, we have some aggregate, and then we have this ring around the aggregate. That ring tends to be highly porous, and it tends to have an overabundance of calcium hydroxide. So you may say, well, what the heck is calcium hydroxide? Cement reacts and it produces two things. It produces CSH, which is the good glue, and it produces calcium hydroxide, which is the other stuff. Calcium hydroxide is soluble, it moves around. So what happens is your aggregate typically has calcium hydroxide on its surface, but it's soluble, it moves around, so you've got a porous ring around your aggregates. It turns out that especially when you're using the lightweight materials, this interfacial transition zone is much smaller to non-existent around the lightweight aggregate particles. And there's probably two real reasons for this. One reason is you don't really have a surface the same way you do on a sand particle because you got nooks and crannies. All right, so just like English muffins that have nooks and crannies that are better at sucking that butter in, right? Here you've got nooks and crannies at your lightweight aggregate, which are greater, will give you greater density in that interfacial transition zone. The other thing that we've worked pretty hard, and I think we've now established, is most of these materials are siliceous. All right, or aluminous, but now you may look at that and say, siliceous, what the heck is that? It's not siliceous, that's a whole different thing, that's TMZ news. All right, siliceous means that it's silica, they're silica containing materials. So happens if you take calcium hydroxide and you put silica with it, you get calcium silicate hydrate, which is that good glue. So what's happening is, you're getting that silica from the aggregate is reacting, but it's only reacting right at that surface, and it's really consuming that calcium hydroxide. So the takeaway is, when you use the lightweight aggregate, this big interfacial transition zone, or bleed channels, goes away, and you see it just kind of drifts in, and you have a very, very small, almost non-detectable interfacial transition zone. So what are some of the benefits of that? Well, we'll skip. I'll show you a couple of the benefits of that in a second here. Generally, you have a slightly lower modulus when you're using the sand in the system. Strength is almost identical. All right, slightly lower modulus. With rare exceptions, the high rise where you're worried about getting a high elastic modulus to provide stiffness, lower modulus is better. So when we're talking about flooring slabs, when we're talking about bridge decks, the lower modulus makes your concrete more extensible. It stretches easier, right? So you think about the fact that you've got stresses building up. If the modulus is lower, the concrete's a little stretchier, all right, than it would be in other cases. So having that lower modulus is not a problem. Now, we know, and this is a little bit counterintuitive because the first thing people think of, there's giant pores in the aggregate, things are going to flow through there, it's going to be dogs, cats, small children going through the system. That's not what happens. All right, what we typically see is that the system is very durable. So they tested some of these big concrete, some people may or may not know this, at one time the US was building these great big ships. These ships were being used in the war effort. After they were done being used in the war effort, a lot of times they've been sunk to become reefs and become coastal barriers. Some of these have actually been cored years and years and years after exposure to seawater, and they are much less permeable than a conventional concrete. One of the reasons why they're less permeable is because we have more hydration taking place, so we filled in that space. The other reason that they're less permeable is this idea that if we've replaced 40% of the sand particles with lightweight sand that no longer has this interfacial transition zone, which is highly porous, it's harder for things to move through the system. So if I were a chloride ion up here, and I had the ability to go through this highly porous network along the interfaces, right? It's very fast to go through that system. We disconnect the porosity because we don't have those interfaces, so you get huge benefits from this in terms of increasing the durability of your concrete, right? Much more dense concretes, when they're hydrated more, this is concrete that ran out of water. Conventional concrete that's just sealed. This is concrete where you've got that lightweight aggregate. Dark spots are pores, holes in the system. There's a whole lot less dark spots down here, so you're getting a much more dense system. These are pictures from NIST. Right? A lot of frequent questions we get. Are the particles porous? Do they increase permeability? Frequently no, because they are very hard to get resaturated with water, and essentially things only move through water in the system, so they essentially become relatively unimportant for the transport property. It's very difficult to resaturate them. We'll get into a couple of the different transport tests, but I guess what I want to talk about here is very quickly, there's really three types of transport tests. There's well, there's 4. I'm sorry, I've got 4 listed, so I should talk about 4. I'll tell you one's not that important in a second. Ionic diffusion, I've got a lot of chlorides here. I've got no chlorides here. Seawall, bridge decks with de-icing salts. It's really the gradient of chloride ions that cause them to move through the system. Capillary suction, the concrete's dry, it wants to suck up water. It's like a big paper towel. Right? Difference between diffusion and suction is the time over which they take place. Diffusion takes years, suction takes days. Okay? Permeation is driven by a pressure gradient. So with the exception of Eric, who has water sitting on one side under huge pressure, nobody else in the room usually has to worry about permeation, although everybody loves to talk about permeability. Right? Permeation is usually not the big driver. And then a lot of times we have drying on one side, suction on another side, and it causes something like a wick. It causes water to move through the system and essentially be deposited. We see, again, x-axis is the amount of light weight in the system. 100% is internal curing. Sorption, the suction of water, goes down substantially because we've increased the density of the system, we've reduced the interfacial transition zone. So we see about half the sorption over a wide range of water to cement ratios in these systems. All right, here you can see a plot. The basic takeaway is the 0.30 water to cement ratio behaves like a 0.23 water to cement ratio when you look at this. So behaving much better than you would expect. De-icing salt, this is a big one when you start to try to show the value. I'm not going to go through all the equations on how we calculate how long it takes the salt to get to the reinforcing bar, but this is the main thing that you use to determine the service life of the system. If it goes in fast, the concrete starts to degrade fast. If it takes a long time, the concrete is going to be long lasting. Right? What we see with internal curing, less penetration of the chloride ions in the system. This is some data from NIST. This is some of our calculations, not surprising. 0.3 concrete behaves like a 0.23 concrete if we measure electrical properties. All right? I will show you a plot later that gets into service life that I think will be much more telling. Freeze-thaw behavior, there were some questions about this earlier. All right? What we've typically noticed is this plot here. Right, we did a big study for Colorado that if you properly air and train your concrete, you will see a plot that is very uninteresting to look at. This is the change in stiffness of your concrete versus the number of freeze-thaw cycles. If it gets to 60%, it failed. The modulus doesn't change almost at all throughout the entire test. This means if you've got the proper air void system, it's very, very durable. One thing we did notice, and I can't explain this right now, I've got some theories that we're working on, we see less scaling with internally cured concrete mixtures than we see with conventional mixtures. ASR, alkali silica reactivity, typically decreases when we look at that in these mixtures. So this was a conventional concrete. We see a lot of expansion. When we replace some of the sand, we have a dilution effect because we have less reactive sand. But when we actually start to look at this, we actually see an additional benefit because of the internal curing. And we see that with 2 different amounts of lightweight sand. So frequently you get a benefit in the system. The real takeaway that nobody is talking about the improvement in service life is when you have restrained shrinkage and corrosion going on simultaneously. So here we have a big steel girder with a 1-foot section of a bridge deck being placed on it. Inside of this we have a very instrumented rebar. So here you can see the rebar. It turns out, if we go back a picture, there's a conventional rebar, a rebar that has lots of sensors in the center, conventional rebar on the other side. We've got a little small notch here so that we know where the crack is going to happen in the system. Right? We did a plain concrete and an internally cured concrete. The plain concrete developed a nice crack. The internally cured concrete never cracked. In the system that was cracked, what we noticed was that not only did water get in through the crack, but it moved for about an 18-inch strip, right around that crack. Those sensors went into corrosion almost instantaneously. right? So we had really dense concrete right here, and this part of the rebar is doing a great job not corroding at all. But this crack, and this crack, and this crack are not only corroding at the tip of the crack, but that crack actually opens up along the rebar about 9 to 10 inches on either side and starts that corrosion on either side. All right, so case study here is one of the earliest bridges. This is the conventional concrete. This is the internally cured concrete that's being placed. All right, what we saw here was no cracking in the internally cured concrete for 4 years. The conventional concrete developed 3 cracks. The only difference between the two, same crew, cast one day after the other, the only difference was the addition of the lightweight aggregate. It's the only difference between the two in the system. Now, it turns out if you go out to this bridge today, all right, you will see that there is one crack in this internally cured bridge, and it's because the girder dropped. They lost support on the girder, so it is a structural crack, not an internally cured crack. You will also notice that there's a big gouge where the snowplow guy got over anxious, gouging both the conventional concrete and the other one. But other than that, this bridge looks incredible to this day. Lisle, New York. I think this is Lisle or not Tonawanda. Did I say that even close to correctly? I've been saying Tonawanda the whole time, so let's just go with it. Essentially, we've got a regular high-performance concrete, the internally cured concrete, almost identical strengths, same amount of air, relatively the same amount of slump. One of the big advantages that you get is you get a slightly higher resistivity, which is because you're cutting off those interfacial transition zones, making your concrete more durable. Right? Again, here we see the mixtures. A lot of times people want to see the numbers on the mixtures. They're here. They'll be in the packet. There have been, to the best of our records, about 300 bridges now that have been constructed with internal curing. Very few of those have I heard. In fact, I can't think of any that have a problem that is an internally curing problem. I can hear a lot that they sent the wrong mix to the job, that they had a problem where it was too flexible, they did something else, the pump operator knew more than everybody else and pumped the concrete 700 feet in the air and dropped it straight down and all the air went away. But that happens in conventional concretes as well. There's almost no issue with the internal curing in the system, all right? Again, as I mentioned, I believe there's been about 300 done. Rapid chloride permeability numbers have been tested, very comparable, if not better. Here you see this is the conventional concrete in Indiana, showing the crack that developed, none in the internally cured deck as we saw before.